Hi everyone, and welcome to Geometry Lesson 2-4, Biconditional Statements and Definitions. A biconditional statement is a statement that combines a conditional statement and its converse. And when we write it in the form P if and only if Q. So for example, I could say, I have homework if and only if I have geometry class. So that would mean that the only time I have homework is when there's geometry class, and the only time I have geometry class is when there's homework. So I like to think of it as something that can be read both forwards and backwards. Now, a common abbreviation for if and only if is IFF, and I know it kind of looks like I spelled something wrong, but I didn't. It is two F's on that. And the symbol for that, instead of just having the single arrow P with the arrow pointing at Q, we use the double arrow to show that it is biconditional, meaning it goes both forwards and backwards. So let's look at an example where we have to take a statement and turn it into some of these related conditional statements. In example 1, we have to take a biconditional statement and write the conditional statement and the converse that it represents. Now, for the conditional statement, you want to keep it in the same order that it's given. For the converse, you're going to switch the order. Okay, so in part A, it says two angles are congruent if and only if their measures are equal. And in part B, it says a solution is a base with the double arrow. It has a pH greater than 7. So pause the video, see if you can do that, and then press play to check your answers. In part A, we would say if two angles are congruent, then their measures are equal. That would be your conditional. For the converse, we would say if their measures are equal, then two angles are congruent. And again, if you wanted to, you could add in a few words. I like to avoid doing that simply because it's more clear that you've done exactly what you needed to do. In part B, the conditional would be if a solution is a base, then it has a pH greater than 7. For the converse, it would be if it has a pH greater than 7, then a solution is a base. Okay? So let's take a look at another example where we're going to, again, try and use this fact of how the biconditional relates to the conditional and the converse. In example 2, we're asked to take each conditional and write the converse and the biconditional statement. In part A, it says if 2x plus 5 equals 11, then x equals 3. And in part B, it says if a point is a midpoint, then it divides a segment into two congruent segments. So pause the video, see if you can do that, and then press play to check your answers. In part A, the converse would switch the order. I would say if x equals 3, then 2x plus 5 equals 11. For the biconditional, I would remove this if that's in the beginning. Right where the then is, I would write if and only if. So it would say 2x plus 5 equals 11 if and only if x equals 3. Okay, let me show you again in part B. For the converse, I would switch the order. So I would say if it divides a segment into two congruent segments, then a point is a midpoint. Okay, and again, you could change the grammar of that. You could add a few words, but I don't like to add too much because then it can be confusing as to whether you did what you needed to. In the biconditional, I would take out the if here. This if would disappear, and then the then change to if and only if. So I would say a point is a midpoint if and only if it divides the segment into two congruent segments. Okay, next we're going to talk about truth value. How can we determine if a biconditional is true? For a biconditional statement to be true, both of the conditional and the converse need to be true. So you need to check both of them. And essentially what I like to do is to read the statement forward and say, if the beginning part is true, does that mean the ending part is true? Then I like to read it backwards. If the ending part is true, does that mean the beginning part is true? Okay, so I like to read it forwards and backwards, and that really helps me to figure this out. Instead of rewriting the conditional and the converse, that's what I like to do. If either one of those is false, then the entire biconditional statement is false. Okay, so if either one is false, it's all false. Let's take a look at an example. In example 3, we need to determine if each biconditional is true. If it's false, we need to give a counterexample. Part A says the square has a side length of 5 if and only if it has an area of 25. And part B says the number n is a positive integer if and only if 2n is a natural number. So pause the video, see if you can figure out true or false, and then press play to check your answers. So part A is true, because if a square does have a side length of 5, then its area has to be 25, because it's 5 times 5. And if a square has an area of 25, then the side length must be 5. There's no other number that would satisfy that. Okay, so A is true. B is false, okay, because if I have any number that is positive, then 2 times that would still be a natural number. But if I have 2n is any number like 3, okay, then the number n is not an integer, because if I divide this, n is going to be 1.5, which is not an integer. Integers do not have decimal areas. Okay, a lot of that is remembering those terms from algebra, okay? So that's it for this video. If you have questions about anything in it, please bring them to class and I'd be happy to answer them.